Okay, so this is a supplementary recording to lecture number 35. In lecture number 35, we have discussed minimum mean square error estimators. And we have found first the optimal estimator. Let me show you the example and then talk about it. So let's try to share that screen. It's this one. Okay, so it is this example. Let me start it from the beginning.
To see this, this is the estimators that I'm trying to sketch on the board. Okay. So higher order estimators are the ones approaching towards this optimal estimator, 1/2 signum.
On this tablet screen, there are some plots, and I'll be discussing these plots in this video. There's a dash line. That dash lines corresponds to the optimal minimum mean square error estimator, and it's very simply 1/2 times signum x. So it's the sine of x times 0.5. So that is that dashed blue line that my finger is right now pointing at. So the other curves, which are the solid curves, are different degrees, different, let's say, estimators with higher order polynomials. Let me go ahead with the video.
X line, okay? So you see mean MSE estimator is this one. And this is the linear estimator or affine estimator. And let's see the errors. So this is the minimum.
So in this video, we will describe, or we will see the Matlab code for the linear estimator, cubic estimator, and the higher order estimators. And we will see how these plots are generated. Okay, so let me switch to the, let's see. Let's switch to the Matlab. So this was the Matlab code that I'll be sharing as a link in the description of this video. So in the first line of this Matlab code, you see the following. Number of the Monte Carlo runs is set as 10,000. Okay, so if I run this first piece, you see 10,000 samples from this bivariate distribution of x. The horizontal line is, let's say, x, the vertical line is y. So I have 10,000 realizations for that, and every realization is marked as a blue dot on this xy plane. Okay, so how do I generate this? Well, Monte Carlo number is 10,000. Then I'm generating in line number 3, 10,000 random vectors whose elements are in between minus 0.5 and 0.5. Okay, so they are uniformly distributed in, it's a 2-element vector, and each entry of that vector is uniformly distributed in between minus 0.5 and 0.5. Okay, essentially, this is one of those blocks, you may say. So this is the uniform distribution, and the length of this side is 1, the length of the other side is 1, so it's a square, 1 by 1 square, and it's uniformly distributed. Okay, so how do I generate these double squares? Okay, on the first quadrant and on the third quadrant. So the way I generate it, as you see, starting from line 5 to line 8, I guess. Okay, so how do I generate this? Actually, this is mixture of two uniform distributions. So I have a uniform distribution on the first quadrant and another uniform distribution on the third quadrant. So how do I generate this mixture? Well, if you check this Matlab code, I generate a second random variable, which is binary random variable, bin RV. And you see that this bin RV is taking values either 0 or 1. And if you check this, the next Matlab code, then bin RV takes values in between -1 and 1. Sorry, it takes either the value of -1 or 1. It takes binary value -1 or 1. And then bivariate distribution is nothing but, combination of these two random variables. Okay. So please check this line 8 and think about it, how we generate this bivariate distribution without any for loops. Okay. So it is essentially a combination, an addition of two random variables which are independent from each other. And please try to remember how do we calculate the sum of two independent PDF of the sum of the two independent random variables. Okay, so this figure number 1 shows us that we can generate bivariate XY pairs with this, a few lines of code. Next, what do we have? Next, what we have is, let me move it to this side. So this is the minimum mean square error estimator. So as you see, estimate for y is nothing but 0.5 times sine of the x. Okay. Then I define the error. So this is the true y value minus its estimate. And that becomes our error for that realization. I have 10,000 realizations like that. And then I calculate the average of those errors, which is called the bias. And then mean square error value of that average of that mean square errors. Okay, which is calculated according to this. And we have theoretical results. Theoretical result is 0 and 1 over 12. So this plot shows us the distribution of the error. So x-axis is the error. So error is in between minus 0.5 to 0.5. And it's again almost like uniformly distributed. Okay. It should be indeed uniformly distributed, but since this is like a finite number of Monte Carlo runs, there is always a deviation from this theoretical result. So bias in theory is this. Bias calculated by this Monte Carlo run, which is line number 20 over here, is this number. It's a fairly small number. And in theory, we have 1 over 12 as the MSE. And Monte Carlo estimate for that MSE is almost identical. Okay. So it's identical to the second digit and very close in the third digit. So this is the optimal estimator. Now let's look at the mean square error estimate, linear MMSE estimator. So this estimator is, as we have derived in class, it has an expression like this. Y hat is equal to 3 over 4, 0.75 times x. So I repeat the same operation. First, I calculate this, the weight, 0.75, using our normal equations, you may say. Okay, Rx is this, Ryx is this, and this is the single weight calculated using this operation. And then I generate my estimate for y according to this relation. Y hat is equal to 0.75 times x. Okay, then again I calculate the error. Okay, then I have a theoretical result. The bias should be 0, and MSU should be equal to, in theory, it should be something like this, 0.14583. So in practice, in the Monte Carlo run, the average for the MSE is, as you see over here, it's again fairly close. Bias is again fairly close to 0. But what we see over here is obviously not a uniform distribution. And the error is changing from -1 to 1. Okay. So we see that we can make very, large errors. In the previous case, in the optimal minimum mean square error estimator, error was limited to -0.5 to 0.5. Now we see that it's spanning a larger range. Okay. So if I increase, the degrees of freedom, and if I have a cubic estimator, meaning that it's this type of an estimator, it has 2 degrees of freedom. W1 is the first degree, W3 is the second degree. So W1 is multiplying x, W3 is multiplying x cubed. Okay. Then the optimal coefficients are calculated as we have studied in class. Okay. Then how do we calculate these optimal coefficients? Again, using normal equations. So this is the calculation for the optimal equations. And again, I calculate my estimate for the cubic estimator, take its difference from the true value for each 10,000 Monte Carlo runs. Then I calculate the average of the error in the Monte Carlo runs. Then I'll calculate the average of the squared error. Okay, so this becomes an estimate for the mean square error. So the results are, as you see over here, so error is a little bit reduced and Monte Carlo run closely let's say, agrees with the theoretical results. But we see that, again, we are making large mistakes with some probability, but somewhat this is less looking like a Gaussian shape, okay? So it's more like concentrated around 0 in comparison to the linear estimator. So if I increase the order one more time, so this is a 5th degree estimator. So error is further reduced, and there is more concentration. And you can see that, you know, outlier errors greater than 0.5 is a little bit less over here. So if I have a 7th degree estimator, and you can see these estimators expressions over here for 3rd degree, for 5th degree, for 7th degree. And for example, for the calculation of the 7th degree, I'm not doing anything else other than, you know, calculating the autocorrelation of the observations. And I am treating x to the power 5 as a new observation. Okay, x to the power, this should be 7 as a new observation, x to the 5 as a new observation. So what is the correlation between these two observations? This is expressed in this matrix. Okay, so pairwise correlations are expressed, and the pairwise correlation with the desired variable y is also expressed in this ryx vector. Then I calculate the optimal weights, and for this one, the optimal weights are, as you see over here. So this is the expression. Okay, so the error is further reduced. So in figure number 2, so you are seeing the estimators that I have shown in the classroom. So these are the estimators. Estimator number 1 up to estimator 7, I guess. These are the estimators in question. And if I compare these estimators, so mean MSE estimator is a dashed line. So this is sine of x times 0.5. So what we see is that the linear estimator is this red line, and the other estimators are becoming a better and a better approximation as the order of the estimator increases. For example, 13th order estimator, as you see this one, this is the solid blue line on which is closest to this, let's say, crossover. Okay, so this one is the 11th one. Okay, the red one, solid red line is this 11th one. So what we see is as follows. For example, this 13th order estimator is oscillating around this 0.5 and minus 0.5. But of course, since this is an odd function, as we have discussed in the classroom, and it's very visible over here, so it's passing from 0. And again, for example, if your observation is 0.01 or something like that, then your estimator is always producing something around 0. But we know that for this value, y can be even 1. So you can get a, errors as large as 1 for the x values when x value is close to 0. So that explains why we have large errors for these polynomial estimators. So if we go ahead, let's see what else do we have. In figure number 3, we see the MSE of these estimators, theoretical results. So we see that the theoretical MSE with the polynomial order, it decreases as expected. But as you see that it won't be reaching the optimal minimum mean square error estimator value, which is 1 over 12, 0.08 something, okay? Because as you can see, this estimator in the earlier figure is a discontinuous function, but all of the other functions are continuous functions. And just because of that, it will be always making a large error when x is close to 0, okay? Because it has to be, continuous around 0, it has to pass through 0 point. And when x is close to 0, you can see that it can be making an error as large as 1, okay? Or minus 1. So that explains these plots. So what's the conclusion? Let's see. The conclusion is, if we can calculate the minimum mean square error estimator, this nonlinear function, that is the best estimator that we can get. But in practice, this can be very difficult to calculate. So just because of that, in practice, we are using linear MMSE estimators, which is this straight line passing through this origin. So its performances, of course, in comparison to the optimal estimator is a little bit poor, but it's an easily realizable estimator. So in some applications, you may have, let's say, cubic 50-degree, 70-degree estimators, let's say polynomial estimators, and so on. So to realize those estimators, you have to have the higher order moments, higher order moments of the observations, like you need to calculate the expected value of the x cube and so on. So if you can calculate higher order moments of the observations and cross correlation of the observation to a, let's say, power, let's say third power of the observation and the desired quantity, if you can also calculate that, you can implement these polynomial estimators. But again, in practice, estimation of the higher order moments is also difficult. So in many applications, we are using linear MMSE estimators, and we are trying to compare our results with the optimal estimators, and we are trying to see the gap. Okay, so that becomes the optimal estimator, theoretical one. If we can calculate it in theory, then the performance gap between those two estimators can be a decision point whether to go ahead with the linear estimator or to try something else. Okay, that's all I would like to say, and that is the end of our supplementary video on lecture number 35. Okay, thank you very much.